to talk about whether a vector field in R3 is conservative or not, we need to introduce a differential operation. So this thing is called the curl of F. Okay, curl of a vector field. So this is a name. Okay, and this is the notation that we see in the gradient. You can see this as a notation for differential operator. Okay, and this is like the cross product, and here you have a function, the vector field F. Okay, so the reason why I use this notation is very similar to the cross product, because the way how you can compute the curl is really just like how we compute the cross product. So when I have vectors in three-dimensional space and I want to compute the cross product, I'll put the ijk in my 3x3 matrix, and now look at what is in my first vector. So this is like a vector differentiating each component respectively, right? Oh, sorry, this differentiate the function with respect to different variables. Okay, so the first one be ddx, the second one be dy, the third one be dz. Okay, then the vector field F has x, y, z components as these functions. Let's call them m for the x component, n for the y component, and p for the z component. Now we take the determinant as usual, except, so now instead of having functions or numbers, we have a differential operator there. So when ddy meets a function p, what this means is we differentiate the p with respect to y. Okay, and then for the y component, for the next one, then we have this. So we have ddz meeting the m function. So you see I have dm dz. And the last one, I'm seeing the differential ddx with the n function. So you see in the z component, I have a positive dn dx. All right. And now we take care of the off-diagonal terms. So over here, I have ddy and m, but it's off-diagonal direction, so it's minus dn dy. Okay, and the next one, this is what we have. So it's ddx of p with minus sign. So dp dx with minus sign. And the last one is this, m with ddz, so minus, sorry, n with dn dz. So that's this, okay? So the only difference I would say is when you see this notation, you will put the vector ddx, ddy, and ddz. And then everything else is the same as how you take the determinant of a 3x3 matrix. Okay, so why is this important? Because the vector field f of x, y, z is conservative, meaning it can be expressed as the gradient of some function if and only if the curl of this vector field is a zero vector, meaning every component is equal to 0. Okay, so if I if I'm given a three-dimensional vector field and I want to determine whether it is conservative, then I go ahead and compute the curl. If the curl is equal to 0, then I can say this is conservative, okay? In a nice looking region. So that's the only case we'll think about or encounter in our class. So this is the only thing that we need to know. All right.